So thanks once again for joining us. Today we're going to be furthering our conversation on the reverse osmosis with systems, with looking now at the pre and post treatment for these systems. So let's get the slide going here. Thank you. So today we're going to be presenting both myself and Taylor. So my name's Tyler Gamble. I'm the General Manager of the Commercial Industrial Engineering Division. And I've got engineering degrees from both McGill and Dalhousie, and I've been working in the water industry since 2010. Taylor has been with the Canada Water Group as well as a sales and applications engineer. And she's been in the water industry since 2017 and has an engineering degree from University of Regina as well as a bachelor's of science in biology. So any bacteria questions, make sure to forward them on to her. About Canada Water Group ourselves here. So we've been in the water conditioning industry for over 50 years in various ways, shapes, and forms. And our whole idea throughout those 50 years was to make sure we provide excellent value to our customers. So whether that's end users who have a water softener or basement for their home, or maybe commercial applications where they need some advanced filtration or even a reverse osmosis system. We want to be able to provide you with that value, whether it's on the selection end, during troubleshooting, install, what have you. So behind that value is having a large team, and we're growing all the time, to provide you with that support that you need right from the start when you're selecting your equipment on your application, all the way down through to startup and troubleshooting at the far end. We're going to be with you every step of the way. So now that the formalities are out of the way, we can get into the meat of the presentation here. So what we're actually going to be covering today, like I mentioned there, is pre-treatment and post-treatment and storage for RO water. Reverse osmosis systems are they're very useful and have become more and more useful as time's gone on, with their costs coming down, but there are a few things that you want to be aware of as we're going through it. So we're going to do a couple of reminders from the last session that play into today. We're going to be looking at pre-treatment goals and sort of what technologies you're going to be looking at to achieve those goals. Then we're going to be looking at post-treatment and storage. So once again, what are the goals that we're trying to achieve with this equipment? And then looking at what the water quality looks like after an RO system and how that impacts our goals, and then also our storage options. And then lastly, we'll finish off with a couple of examples. So just a quick reminder from the last session, if you were able to join us, and if you weren't, by all means, go back in there, take a look at that video, it's great, and then maybe sign up for our webinars again, just so that way you don't miss a session. But reverse osmosis systems are looking at removing things in the ionic range of our molecular scale here. So there's a whole pile of molecules here and that sort of thing, but RO really shines at removing those small particles. Anything larger than that, we really want to try and remove before we have the RO sitting there getting the water and then providing us our production water as well. So anything like colloidal clay, oxidized iron, oxidized manganese, all sorts of other things in there, you want to really make sure to try and remove those before you get into the RO system. Secondly, just as a quick reminder here, so in terms of water quality, what we want to actually look at, what does the RO want to see for max and mins and those sorts of things? The ones that you really want to focus in on here are a couple of them. And that we'll want to review basically the max iron, maximum manganese. We really don't want any hydrogen sulfide. Water hardness has got to be less than a grain. Oils and organic tolerances, obviously, once again, 0, as well as free chlorine within the water. We don't want any of that in there whatsoever. And those are all usually pretty well available, regardless of what your testing method is. Whether you're taking your own test, those tests are all pretty easy to find. Maybe not the oils. But the one of which in particular that you might have trouble finding is the silt density index, and it's basically a metric that sort of explains the filtration properties of the water, for lack of a better term. And that's one that's really hard to find, but usually you're looking at colloidal clays and that sort of thing is where that guy fills in. So if it is something that you are worried about within your water, you may have to ask specifically for that, and then take additional pre-treatment steps to get rid of it. So in terms of pre-treatment, so what are the goals? So the goals of the pre-treatment, really, we want to remove the contaminants that adversely impact membrane longevity and performance. And that's a big mouthful. Basically, it says that we want to remove contaminants that are going to make our RO run not that well. So would mean low recovery rates. It could mean low production. It could mean low lifespans. All those sorts of things play in. So there are kind of three general spots that play into that. So it can either, our membrane performance can be impacted by, like I said, generally three things. So membrane fouling, which is basically plugging of pores. So that can be minerals. It could be a bunch of different things. Oxidation of the membrane. So that meaning things like chlorine, ozone, hydrogen peroxide, those sort of things we want to make sure to remove out of the water before the membrane itself. And then lastly is biofouling. So there's kind of a quick way to remember all these things, is that you want soft, clean, and clean meaning both particles and bacteria, and dechlorinated water. And the big thing about that is you always want that going to the RO system. So if there's ever time when your filters are down for backwash or generations, what have you, you'll want to make sure that there's some sort of communication mechanism between your pre-filters and your RO system, so the RO is not running, or you're going to size your pre-treatment to be able to handle that flow rate all of the time. So in terms of pre-treatments of concern, we can kind of look at them in two groups once again. We're either looking at suspended solids, so that's a very large group, but you can, most of the times when we're talking about well water or municipal water, we're looking at turbidity, we're looking at particulate iron, we're looking at particulate clay, could be looking at silt or colloidal clay, particulate manganese, and then silt or colloidal clay. There's probably a few others I'm forgetting, but anything that you can see with your eyeballs when you're looking at the water and there's something there, you want to remove all of that. And then in terms of dissolved contaminants, these might be things that add color to the water, like organics, or it might be something that does scale buildup, like hardness. And then it's also anything that could oxidize the membrane, so damage the membrane itself. So example, free chlorine is a big one. So we'll start with the filtration, so suspended solids and that sort of thing. So we want to remove these from the water. So there are a few different technologies that we can use to achieve that. One of which, when we're talking about kind of the big three in terms of filtration from wells, is iron, manganese, and hydrogen sulfide. So there you've got a few different options. Green sand is one, chem-free is another, and berm is another. The one thing that you'll want to watch out for with things like green sand, obviously, is that normally there's some sort of oxidant role being played there, so you want to make sure that that's not making its way to the RO. Chem-free systems do pretty well, but you've got a lot of dissolved air in there you're probably going to want to get rid of somehow. And then lastly, berm works well typically on smaller applications, but generally speaking, commercial, we're seeing one of the first two, or a Philox or a Catalox or something like that. For next sand and multimedia, that's where we're looking at specific turbidity removal. So that'd be like the silts that I spoke about earlier. If you already have or are already oxidizing your iron and your manganese, then next sand and multimedia filters work great, along with any other sort of chunks and bits of things that you can find in there. And then lastly, in terms of filtration, what we kind of group in the last one here, but it's really targeted towards the dissolved side, is the activated carbon. So for example, if you had a green sand system up front that you were feeding chlorine into to remove your iron and your manganese, well, then you've got to figure out a way to remove that chlorine, and usually activated carbon is our best method, even if there are other options available out there. But activated carbon is kind of a tried and true one for doing that. And then depending on the types of organics, activated carbon might also be a good fit. So in terms of little accessories and that sort of thing that would go along with your filtration equipment, I kind of alluded to a little bit of them, but number one would probably, that you see most often, are probably chemical feed systems. So basically those are usually a combination of a chemical feed pump and some sort of chemical tank like you see in the picture there. And then its job is to dose, whether it's an oxidant, a coagulant, or something of that sort, into the water. So that way you can remove, so that either you can take dissolved contaminants and make them oxidize, or maybe coagulate some organics together, or maybe you've got another purpose altogether. Maybe you're adjusting the pH. A bunch of different ways you can look at it. Typically, they're operated one of two different ways, either volumetrically, so tied in with some sort of flow pacing mechanism, so that way the dosing always matches the flow that's going through the system. Or if you know your steady eddy, your flow rate's never going to increase, decrease off of this one number, then you can kind of reliably go with an on-off operation. Whether that's tied into the RO, maybe that's tied into the pressure switch for the pump that's providing it. It's a couple different ways you can do it. Along with those chemical feed systems, you may or may not need this, but a lot of times we do recommend it, is some sort of mixer or contact tank and that sort of thing. So that kind of what it allows you to do is make sure that your chemical solution that you're adding, oxidants, coagulant, whatever, is thoroughly mixed and then evenly dispersed throughout your water. So that way you get the best reaction available to you. And what's nice about the contact tanks is that they do provide you some contact time ahead of that. So if you are dealing with a particularly stubborn contaminant, that gives you additional time there. Whereas the inline static mixers, generally speaking, use for higher flows, and then you may need some storage thereafter. In terms of organics, there's a couple of different ways to go at it. Some people are pretty convinced and go by this successfully, is that they'll actually remove organics with ROs. We tend to lean away from that only because organics tend to gum up your membranes. So we like to remove them ahead of time. So we can do it in a bunch of different ways, as we kind of talked about. So anion exchange, so tannin filters, as they're also known as. Carbon filtration might work depending on the organic you're dealing with. Enhanced coagulation, oxidation followed by carbon filtration. There are a bunch of different methods, and there could be we could do a whole webinar on organics and how to remove them, but that's not today's topic. But it kind of gives you an idea that we really want to be removing that ahead of time. So now that we've talked about the filter side of it, now we're going to look at kind of the big bad one that everybody talks about, which is hardness. And before I get into that, some of you may be aware that similar to organics, some people are starting to lean towards using RO systems, basically to soften the water, and that is remove the hardness from the water. You have clean water afterwards. Generally speaking, we like to stay away from that from a best practice point of view. Hardness has a tendency to scale up membranes, and so basically you'll be replacing membranes frequently, but also the scale build up inside the RO before the membrane is going to be significant as well, because you're concentrating your hardness to the point where it's going to easily scale anything. So you end up with a lot of maintenance issues that are best just avoided. So let's deal with the hardness appropriately by either softening the system or adding anti-scaling. We're going to go through both here because they're both pretty important. We'll go through softening first, so you can see the picture on the left there. So it actually replaces the hardness minerals with in the feed water with sodium, with using a softener as I recommended. There are advantages to this. It's easy operation. A lot of people know how softeners work already. They're not that difficult to run. It's really easy to tell whether or not the system is working. You can take a quick test and then you see the water's either soft or it's not. So then you know whether it's working. And then softener salt is also easy to find at any grocery store, hardware store, wherever. In terms of disadvantages, there are a few when you compare them to anti-scalants. Usually it's a higher CapEx and higher OpEx, so meaning that it costs more to purchase the equipment up front. And then it also might cost you more in the long run. This really gets apparent in the much larger RO systems when you're dealing in applications where the feed water flow rates are in excess of, say, 15, 20, 25 gallons per minute. There, at that point, the difference makes a big deal. And then also when you get into those higher flow rates, a larger footprint is needed for the softening equipment. So generally, when you're looking at installing this equipment ahead of the RO system, we're going to take the example of the city water main here. You're going to have your carbon filter, which is going to dechlorinate your water, which will also help out your softening resin in terms of oxidizing it. Then you have your twin alternating softener in this case, meaning that it's always going to have, you're always going to have soft water 24/7, regardless of what's going on, and then that feeds the RO system, and then it goes out to service. So in terms of the other other guy in the room, anti-scalant. So what it does is not removing anything, it's sequestering it. So it's kind of the chemical we're adding with the chemical feed system is binding itself to the hardness for a given period of time. So its advantages are, I mean, you saw the chemical feed system I pictured before. It's a pretty small unit, which is really important when you get to those larger flow rates. When compared to a softener, and the CapEx and the OpEx are also a lot lower. Typically speaking though, in terms of things that are a little bit drawbacks, you're not really quite sure if it's working right that very moment, because depending on what equipment you have there, you may have a flow indicator on your chemical feed, but you may not. So you'd have to do some math, compare your feed water flow rates with the amount of chemical you're going through, do the math out and figure out, are you dosing appropriately based on what the manufacturer recommended. It also requires specialized chemicals that may or may not be easy to get a hold of when compared to salt. And then you do want to make sure that whoever is working that is trained appropriately and is continuously monitoring this equipment. I mean, that goes for softeners too, but it's especially important on the anti-scalant. And then the last bit is that sequestration of the hardness minerals doesn't last forever. So you got to make sure that you're paying attention to when you're selecting your RO system, you may want to pick one unit over another. So this would be what your system looks like when you sort of compare it to the other system before. Here we have the same filter that we had before with the lockout switch to make sure that our RO doesn't run when there's chlorinated water running through. And then we just have our chemical feed system, an inline mixer, and then to the RO. So there's a lot less equipment visually and then also on the floor as well, especially in this application. But the size of the equipment kind of depends on how big your RO system is. So now we'll get into post-treatment and storage. Where really the goal of everything that we're trying to do here is we spent all this time and money and effort pre-treating the water, running the RO. Now we want to make sure that that production water that we got, that low TDS water that we have, is now going to be, we want to store it in a manner that we can use it in that form, because ROs typically have a very slow output. So you may not be able, you may have to store it so that way the RO can continuously run, and then you use the water intermittently. So typically the water quality out of an RO system, it'll be a lower pH. And I say typically because there are exceptions to the rule, but this is generally speaking what you can expect. So the pH is going to be lowered, typically not quite to a orange juice level, but we're talking if it's at 7, 7.5, you're probably looking at 6, 6.5. Drop it about a point, maybe 2, depends on your water. You're going to lower the TDS obviously. And then the combination of those two is going to give you a low or negative Langmuir index. A Langmuir index, for those of you not familiar, is a measure of the corrosiveness of the water. And negative Langmuir index means the water is going to try and strip away material from your plumbing, equipment, and that sort of thing. A positive Langmuir index means there's a tendency to be scale forming. Corrosive water, and some of you may have already experienced this, is very bad for copper and brass. We've heard stories about whole home ROs where somebody didn't do their homework, didn't add in the proper post treatments, and next thing you know, their entire basement is starting to have little leaks in the ceiling because of all the copper that was starting to get pitted. And this won't be something you notice right away. It may take 6 months or a year, but it's going to happen. So the big question is how do we deal for things like that? Well, it's pretty simple. I mean, we'll just raise the pH and TDS. So there are usually a couple ways to go about this. First one here is pretty simple. It's just a inline remineralizing filter, usually filled with some sort of calcite or just pH raising material, and that'll add a little bit of hardness and back to your water. The only problem is you really don't have control over how much mineral and pH correction you're actually doing. So if you're in a spot where that's important, then this probably isn't the best one. You may want to go to a chemical feed system. So there you can actually dial it in, so that way you've got precise control over the pH and or TDS addition. So if you're looking to do both, then you can do both. If you only want to raise the pH, then you can add something like sodium hydroxide, which is going to raise the TDS only slightly, but you won't be adding any hardness back or anything like that. Chemical feed systems are going to be more costly than the remineralizing filter. but once again, you get that control. So it's kind of the trade-offs. What do you want to do? The other thing that we want to be aware of is the bacterial contamination and storage. So we can deal with that a couple different ways by either adding chlorine into the storage tank, or maybe we've got a UV system downstream, but we'll kind of get into that in a second here. So things that we want to consider regardless of the storage type, because there are a couple and we'll get into them here. Bacterial disinfection if it's needed. I mean, if the public's drinking this water, and depending on the regulations within your area, you may need to add another level of disinfection outside of the RO system because it's going to remove a lot, if not all of it already. Material compatibility downstream, we kind of spoke to that a lot. I gave an example there. So you want to make sure that all your plumbing and equipment downstream is all either stainless grade, PC, that sort of thing. Make sure that the material is compatible so that way the RO won't try and get its friends back, so to speak. And then also, what's your intended water quality for the application? That last one is going to dictate your first two. If you're just using processed water and nobody's ever going to drink or touch this water, then you probably don't need the disinfection. And depending on what you need downstream, if like car wash spot-free rinse, for example, you're not concerned about bacterial disinfection, but you are definitely concerned about providing low TDS water. So you're going to choose materials that will work well. So here we're going to get to two types of storage. We're going to discuss them. One of which is the atmospheric storage, and the other one is storage under pressure. And please, if anyone has a good Queen joke here, let me know. Send it to me so that way we've got it, so I can add it to the next presentation. So in terms of the RO water, when we're dealing with atmospheric tanks, we're like, once again, we're going to be storing these tanks under atmospheric pressure, not pressurized systems or anything like that. So RO system usually is turned off on and off by a level switch that's in the tank. Sometimes you see a float in there. Sometimes it might be a couple of rods that have different heights on them. They're a bunch of different places. But generally speaking, is that the level of the water in the tank is going to dictate when the RO turns on and off. In smaller applications, commercial applications or whole home ROs, usually the general guideline is 24 hours worth of storage. When you get up to larger systems, you have to sort of break that rule a bit to however it makes sense. In terms of advantages of atmospheric systems, you can store large volumes of water under a smaller footprint when you compare to pressurized systems. Ideally, your tanks are available locally in all sorts of shapes and sizes. So if you've got a weird location in a basement where the doors are narrow and that sort of thing, you can talk to one of those storage tank fabricators, and they can usually come. They probably have an option for you. And then the other big bonus of this side here is that because you've got a lot more storage and you've got and you're going to have to repressurize the water, now you can pick a pump that'll match whatever output you've got. Disadvantages on this side here too is that you actually need additional equipment for pumping. So this adds additional floor space, cost, and that sort of thing. And then depending on your storage tank that you've got there, you've got the possibility of bacterial contamination. You can sort of get around that by adding in what's called a hydrophobic vent, but that still may not be enough depending on your area and the regulations required. So in terms of just a little line drawing here to get you an idea of what's going on, so you've got your RO system on the left-hand side here, then it goes into your pH filter, which is correcting your water in this scenario here. You'll then go into your storage tank, which in this case here, just a great big rectangle as it's shown there, but you see that there's a level float there that goes back to the RO. We've got our distribution pump, and then we've also got our 5-micron filter before the UV. The 5-micron filter is listed there because most manufacturers recommend, regardless of water quality upstream, that they need that in front of their UV system to make sure that the UVT is appropriate. Now, we'll get into pressure tanks here. So here we're actually going from the RO directly into a pressure tank instead of your atmospheric one there. So there you're turning on and off the RO with a pressure switch. And it's used in scenarios where the RO is, generally speaking, designed to match or exceed the flow demand of the application. A good example of this would be humidifiers. Generally speaking, their demand is pretty low in terms of water. So generally we would go and size the RO appropriately there so that way it could just feed the humidifier directly, but you still want a pressure tank in there to buffer out the on-off cycles, but also provide a little bit of volume, just so that way there it's a bit of a safety. When the system first turns on, you're not worried about the humidifier not getting water in the delay. So advantages is that because the water's already under pressure, you don't need any additional pumps. Disinfection is typically not required because you're not actually introducing another medium to the water. In the example of the atmospheric tank, as the water level rises and falls in that atmospheric tank, air is pulled in and out of the tank, so there is the ability for bacteria to get introduced in there. With a pressurized system, because it's all tightly sealed, as long as you've disinfected your system ahead of time properly, you don't have to worry about that. Disadvantages is that in comparison atmospheric, you've got low volume of storage unless you want to bank a whole pile of pressure tanks, but that gets expensive. And then the back pressure that the pressure tank is adding can reduce your RO output. But usually that's one of those things that's not a huge concern because once again, we're making sure that the RO is sized to match that back pressure. So in terms of how it can look like, here I've got a special example here, but for the most of the time, what you're going to see is just the RO system itself here on the left going directly into a pressure tank. In this scenario here, they needed a little bit more water than what the RO could produce if it needed to. So then we just added a little demand pump and a second pressure tank, gives us a little more storage. But we didn't, in this scenario here, that's all we needed. Typically, you would probably just find a single pressure tank there, and then you'd have your volume there. You'd have your ability to push a little bit more water if you need it. But so with that, I'm going to hand the reins over to Taylor, and then she can give you a couple of examples here.
All right, I think I'm here now. Tyler, I'll just get you to give me, oh, you gave me control, perfect. Okay, so I'm Taylor. I'm going to be going over the sizing examples with you guys. So just to be clear from the start here, we will not be going over how to size the RO systems. We already did that in our last webinar, so you can check that one out. Today, we're just going to be going over how to pick and choose your pre-treatment and size it appropriately for an already sized RO system, and same with post-treatment and storage. So let's start with that. Tyler, I think you took my control away now. Okay. I have controls again. Okay. So I'll start with this one. A resort hotel in Phoenix, Arizona is using reverse osmosis water for their ice machines, their restaurant, food, and beverage production. So we're working with the City of Phoenix municipal water supply in this case. They are going to require 24/7 operation from the RO system. So the RO should be able to produce water for them 24/7. In this case, space is limited. So we're working with a small footprint. And the daily usage here is going to be about 2,000 gallons per day. However, the RO will be sized to keep up with about 3 gallons a minute continuously. So in this case, we're going with a 3 gallon a minute RO system, an already sized CAN 4040-3. So the first thing we want to consider when we're choosing pre-treatment is what is in the water that we should be removing. So City of Phoenix water, if you don't know what's in your water supply, you can always Google it. Typically, municipalities will put all of their water reports online for public use. So if you're ever unsure, you can always look it up, and that's what I did here. So the City of Phoenix uses chlorine as an oxidant, same with chlorine dioxide. So those are things that we're going to want to get rid of before the RO system. And they also have water hardness. So their hardness is about 10 to 16 grains per gallon. We can compare this water report to our feed water guidelines. So the guidelines that we'd like to see before the RO system, we'd like to see less than 1 grain per gallon, so soft water, and we'd like to see no chlorine. So when we're sizing pre-treatment, we want to make sure that it's sized to keep up with the feed flow rate of the RO system. So for a 4040-3, that's about 5 gallons a minute. So all our pre-treatment must be sized to handle 5 gallons a minute. For the chlorine removal, we're going to want to go with an activated carbon filter, sized for 5 gallons a minute. And in this case, because we're dealing with space limitations, we're going to go with an anti-scalant system instead of a water softener for the hardness. So that includes a chemical pump and a solution tank, and these will be sized to handle the 5 gallon a minute feed flow rate to the RO as well. There's just a picture showing some of the anti-scalant that we normally deal with by Tech 3000. Okay, so here we have a pre-treatment flow diagram. So this is kind of our setup here with our carbon filter and our anti-scalant for the RO system. So you can see the 5 gallon a minute feed flow rate that we're trying to achieve. Anti-scalant system is going to go right up front of the RO system. And then before that, we've got our activated carbon filter. So for 5 gallons a minute, for this case, I'm going to choose a 14-inch single carbon filter, and it's going to have an RO lockout switch on it since it's a single. So whenever it goes into backwash, it's going to signal to the RO system to stop running during that time, so we don't get any chlorine to the RO membranes. Having trouble changing them again, Tyler. I think you took the controls again. No? Okay, maybe give it a second here. Okay, we're working now. Post-treatment. So we got our pre-treatment figured out. The post-treatment is a little bit different. We're going to size it to keep up with the 3 gallon a minute product flow from the RO system. So this case, the RO is sized to pretty much produce at the rate that they need. So we don't need a ton of storage. Plus we're limited for space. So we're going to go with an 80 gallon pressurized storage tank here. And since this is supplying drinking water for the public, we're going to go with the UV system as well. So that's going to be sized for the 3 gallon a minute feed product flow from the RO system. And then we got another flow diagram here. If I can get to the next slide. Here we go. So this is the post-treatment after the RO system. So we got a 3 gallon a minute rate coming out. That's going to go right into our 80 gallon pressure tank and then through our UV sterilizer before it goes out to service. It's always a good idea to have a 5 micron pre-filter in front of a UV system, even if it's after an RO system, just because you never know. But just to be safe, just to protect the UV, but it doesn't show it on this diagram. So we'll just pretend that it is there. That's pretty much the pre and post treatment for that small application. We'll get into a second one here. This is a little bit larger. A seafood processing plant in the town of Bay St. George, Newfoundland requires low TDS for their equipment rinsing. So the town of Bay St. George municipal water supply is what we're dealing with here. This is only a 16-hour per day operation, so we don't have to worry about continuous operation. We do have some downtime. There's no space limitations to deal with here, but we do have some copper or brass piping and fittings on site to take into account for our post-treatment. So we're going to go 3,500 gallons a day of RO water required. The CAN 4040-4 system has been chosen, which usually produces around 4,000 gallons per day. So first thing, again, we want to look at is what is in the town of Bay St. George municipal water. I did a quick Google search again and came up with this report. So you can see that their TDS is a bit high, so that's why they're after their reverse osmosis system to bring that down. We've got 17 to 18 grains per gallon of water hardness that we're going to have to figure out. And the turbidity levels are also a little bit too high for the RO system. On top of that, it's not shown on here, but they do have a free chlorine residual in their water. So we're going to need to take care of that as well before the RO system. So we can compare this to our feed water guidelines again, and we can confirm that we will need some sort of filter for the turbidity removal. We'll need something to help with our water hardness, and we will need a carbon filter or some sort of filtration equipment to remove the chlorine before the membranes of the RO. So let's move on to that. So in this case, I'm gonna choose a multimedia filter for the turbidity removal. I'm gonna choose an activated carbon filter for chlorine. And we're gonna go with the water softener in this case for hardness removal. There's no space limitations. They're more comfortable with water softener. Pre-treatment in this case must be sized to keep up with the feed flow rate of the RO system, which is 6 gallons a minute in this case. And it also needs to be sized to take into account any other pre-treatment that's downstream from it. And I'll get into that a little bit more on the next slide. But something to first consider is what order do we want this treatment equipment in? So I put together a little flow diagram here. I always like to start with multimedia first. It's good to remove all the turbidity to protect the carbon filter and the softener from having to filter that out, as well as doing their intended job. If you can put your carbon filter in front of your softener, that will not only protect the RO membranes from chlorine, but it's also going to protect your softening resin from chlorine. So this is the typical order that you would want this equipment in. Now, usually when you size this equipment, I find it's easiest if you size the system that's closest to the RO system, so the softener in this case, and then work your way upstream. So we'll start with the water softener sizing. It needs to handle the 6 gallons a minute flow to the RO system. So it's sized for 6 gallons a minute feed. Based on that, along with the water hardness and the daily water usages, we're going to choose a 3 cubic foot twin alternating softener. This softener requires 5 gallons a minute to backwash. And if you're familiar with twin alternating, these will regenerate at any time of the day. As soon as they run out of capacity, no matter what time it is, they're going to do a regeneration. So that we have to take into consideration when we're sizing our upstream filters. So the carbon filter, for example, is not only going to be sized for the 6 gallons a minute flow to the RO system, it's now also needs to handle the 5 gallons a minute backwash flow rate of the softener. So we're going to size our carbon filter for 11 gallons a minute. In this case, I'm going to go with a 14-inch duplex parallel flow carbon filter. This one requires 10 gallons a minute to backwash. Now, like our carbon filters, our multimedia filter also needs to be sized to handle not only the 6 gallons a minute to the RO, but the 5 gallons a minute backwash on the softener. I'm not going to worry about the 10 gallons a minute backwash flow rate on the carbon filter, because these filters, the multimedia and the carbon filter, are both going to regenerate based on time clocks. So they're not going to regenerate just at any time throughout the day. They're going to backwash every couple days, maybe every 2 to 3 days at 2 a.m. or whatever time you want. You can stagger them so they never go at the same time. So as long as that multimedia filter can handle the 6 to the RO and the 5 for the backwash on the softener, we're good to go here. So we're going to size that one as well for 11 gallons a minute. And based on that, I'm going to go with a 16-inch single multimedia filter. I'm going to include an RO lockout kit because it is a single. So when that one backwashes, we have to make sure that the RO does not run during that time. So that's our pre-treatment flow diagram. Let's move on to the post-treatment now. So if you recall, they do have copper or brass fittings and piping present. So we have to make sure that we are adding a little bit of minerals back into the water, raising the pH a little bit, just so that the RO water is not so corrosive on their piping. So we're going to use a calcite filter, and that will be sized to match the RO product flow, which is about 3 gallons a minute here. For storage, we're looking at a large 2,000-gallon atmospheric storage tank. They'll have a float switch in there, which is connected to the RO system. So whenever the tank is full, make sure the RO shuts off. And then we've got a repressurization pump after the storage, which is going to supply 10 gallons a minute of water to the facility. In this case, they've also opted for a UV system since they are disinfecting their equipment, which handles food processing. So they're going to choose a UV system to disinfect, and this will be sized for the 10 gallon a minute. It'll go after that repressurization pump. So I have another flow diagram here for our post-treatment. As you can see, we've got 3 gallon a minute coming from the RO right through the calcite filter to add some minerals back in before it goes to our storage tank. From there, it's repressurized to 10 gallons a minute, where it goes through the UV system, and then it's off to the fish processing. So that is my last example here. To conclude on everything today, your pre-treatment is critical for the performance and the lifespan of your RO membranes. Soft, clean, and dechlorinated water should be present always. So 24/7. If it's not available, you should have some sort of communication to make sure the RO isn't running if your pre-treatment's not doing its job, or if it's in backwash. There are various filtration technologies to remove physical contaminants, ion exchange, carbon filtration to remove dissolved contaminants. So that's for softening, removing chlorine, and hardness can be removed with softeners or sequestered via anti-scalant. The difference between the two depends kind of on the application, space limitations, water quality, all that stuff. And the pre-treatment must be sized to handle the feed flow rate of the RO as well as other upstream equipment. So for example, with the softeners backwashing, your upstream equipment has to be sized to handle that as well. Post-treatment conclusions, RO water is generally corrosive. You can add minerals back into the water with a calcite filter or chemical injection, or you can blend your water with raw TDS water so that you can get it back to acceptable levels. It's less corrosive on your copper and brass plumbing materials. Your post-treatment is going to vary as well depending on your water source and the needs of the application. For storage, we covered 2 methods, atmospheric and pressurized storage. Atmospheric allows for larger volumes of water to be stored. It takes up a larger footprint typically, and you'll need a pump in order to deliver that water to your service line. For pressure tanks, you don't typically require additional pumps. It's already pressurized, but storage capacity and delivery is lower in consumption. So I think at this point, we'll open it up to questions. So if anyone has any questions, you can comment in the chat, or I'm not sure if you can raise your hand on here or not. Tyler, do you know?
I believe there's a way, but typically before we've just been doing questions in the chat. So far, we don't have any, so you and I must have done a perfect job, as always.
As expected.
Yes.
If anyone has,
it's going to say the other thing. If anybody just wants to jump in and ask their question verbally, feel free to do so too.
Yeah, and if no one has any questions right now, you can always reach out to Tyler or I. If you think of something later on, our emails and phone numbers are posted on the slide right now. Tom Matt said, I strongly recommend adding a HEPA or a HEPA filter on open storage. So I believe that is the storage filter that you can put on an atmospheric storage tank that it's like a filter vent that allows air through, but it prevents microbes from entering the tank. So it helps prevent the buildup of microorganisms in your storage water.
Exactly. I mentioned when I said hydrophobic vent, that's essentially what I meant before that. It's basically a specialized air filter that prevents particles and therefore bacteria and viruses from moving in and out of the tank. So that is an option, and that's one of those things that we can provide on request. So I do see there's a question here from, scrolled up a little bit, from Fauzi. What would the requirement for drainage for backwash systems be in rural areas? Very good question, but also very application dependent. A lot of the water that is going to be wasted, whether if it's coming from the RO, is high in TDS. If it's coming from the pre-filtration equipment, depending whether it's a softener, once again, high in TDS. From the filters, it would be high in TSS, so total suspended solids. Really, that's application dependent. And then you also have to take a look at whatever if there are bylaws that you have to adhere to as well within that area.
very water quality dependent. Contaminants such as arsenic, for example, and even arsenic filter. Most places you can't just dump that drain in an open field or something like that. You have to dispose of the waste properly.
So Ken here. So he's asking a question here, and I don't necessarily know the answer off the top of my head, but Ken, we could probably get back to you. But he's asking, can we convert calcite to aragonite pre-RO? Or is he telling us? And then the RO is rejecting the aragonite. I'm not that familiar with aragonite, I guess is how it should be pronounced there. I'm guessing it's some version of a hardness mineral that might tie into something that I didn't address, but we'll call it emerging technologies are the systems that convert the hardness from scale forming types to non-scale forming types. We don't deal with a lot of that here. We're typically we're sticking with the tried, tested, and true methods, I guess at this point. But I mean, there's always developing techs all the time that if they convert the hardness into a non-scale forming type, then that would be a suitable alternate as well. I just don't know how much. I think there's a little bit of research done onto their efficacy, but I think there's still some, I guess, debate, we'll call it, as to how well some of them work and how poorly some of them work, I guess, for lack of a better term. Okay, yeah, so Ken just wrote back, aragonite is the result of altering the structure of calcium carbonate. So yeah, so kind of what I had mentioned there, that there are technologies out there that they're not water softeners, they're water conditioners is the best term for them. And what they're doing is they're altering the structure of the hardness, and so that way it doesn't do any scale forming. Once again, there's emerging research coming out on them as to their efficacy. I have heard the odd time of some of people using an RO systems and having good results, but then I've also heard about those kind of systems being completely ripped out because they didn't work at all. So it's kind of a toss up there. You see, there was a hand raised and I missed it. Oh, Richard raised his hand. So Richard, if you want to go ahead. Or maybe that was a thumb slip, Richard. Might have to give you controls. Okay.
Okay, can you hear me now?
Yes, we can, Richard. Go ahead.
Okay, I've got to do a system with the anti-scalant, and I don't think that we put in any type of mixer, and the water is about 70 grains hard. So I would need to do the mixer because we've got the multimedia, chemical feed pump, and then going right to the RO. So from what you're showing today, a mixer is crucial, or?
Probably the best way to frame it is best practice. I don't know, Taylor, if you agree.
Mm-hmm.
Yeah, best practice. The key thing, and this goes for any chemical feed system, make sure it's dosing as often as possible. So I mean borderline continuous, because continuous means that you're probably lacking, but as long as you're continuously dosing, your solution is going to be mixed well. And then try and put that as far upstream from the RO as possible.
Okay, so you want to do okay. I'll talk to Tom and maybe we'll have to add one because I don't have a mixing tank or a mixer, but I think the mixer would probably work better. But I'm almost positive that it's going to be working directly off of the pressure switch. So as the pump is pumping, it's going to be mixing.
Yeah, and with our RO systems as well, because of the 5 micron pre-filter that's built into the RO, you are going to get some mixing in there as well. So once again, it's best practice. Is it absolutely required? I would, once again, you can kind of say yes or no, but I would say it's best practice. If you don't have the ability to do it or the funds to do it, then by all means.
And then the other question. Oh, sorry.
Sorry, Richard. I did have it as optional on one of my examples, because again, it kind of just depends on the installation and the application itself. So I think in a lot of cases, it would be optional, but I would definitely say best practice.
Well, this is a residential home, so how much is going to be used? So I would imagine I will reach out and we'll put a mixer in. The other thing is that in some applications, I've just used the 5x20 pH tank, and then I've used a 9x48. And on a bigger system, I found that the 9x48, it used up a whole cubic foot of the mineral in a year. So I know we didn't really mention, we just said to keep adding some in there, but maybe make a point of how do you double check? You just check your pH coming out to make sure that it's stable, or?
Yeah, good point. Best way to do that would be, yeah, whether it's if you've got little pH papers that you can pick up at pool supply houses, then that might be your best way to do it. Also, shining a flashlight on the tank itself, if it's a natural colored tank, then you can do that too. It'll give you a good idea of the level. The only thing I would advise against with the pH, I won't say advise against, but just be aware of with the pH paper is that with the filters that the water's just passing through, is that if you measure the pH immediately after you start flowing water, chances are the pH is going to be much higher versus without obviously anything between your testing and your filter, versus if you let it run for a little bit, flush out that high hardness and high pH level, then you'll get a more accurate, well, maybe accurate reading is not the right term, but you'll get a more sort of service oriented pH level.
Okay. All right. Thank you.
You're welcome. See, Fauzi's back with another question here. It says, when you have methane, 24 liters per cubic meter exceeds the setup, what would be the solution? For, you know what, Fauzi, for specific things like this, why don't you reach out to us directly? That's probably the best thing, because we're probably going to have a lot of follow-up questions, especially for something like methane, which, I mean, that's a gas, so we wouldn't want an RO taking a look at it either. Okay, so Ken's back with, yeah, aragonite is the crystal form. And then Fauzi here's got another comment. Cost of the RO unit and infiltration bed shall be balanced out with the cost of the treated water storage tank. Would your recommendation in terms of the rule of thumb and scale? Just trying to figure this out here. I guess maybe Taylor, if you understand this better than I do, you can answer.
Yeah, I was just going to say I'm also having a hard time understanding this question. Maybe we can have another phone call, or and if you want to send us an email so we can just understand exactly what this means so we can answer it better, because I have a hard time understanding what that means as well,
Yeah.
Tyler.
Alberto asks, do you ever need to do TDS blending, so raw water is blended with RO to achieve a specific TDS overall? If so, does your RO unit automate this, or do you have to add on pieces? I know some people simply use ball valves, but I'm curious to your automation. That's a really good question. And probably the best way is that this can either be really simple or really complicated, this whole blending idea. You can be as simple as, yeah, to your point, just a little blending, like just a little ball valve that they have cracked open. The one thing you would need to add is some sort of solenoid valve to make sure it closes that line when the RO is not running. Otherwise, that blending valve is just going to continuously push water to your storage. You don't want that. That is only going to be as reliable as your pressure is stable and your raw water quality does not change. So if you have any doubts about that side of it, then you actually need something that's way more complicated and probably involves a PLC and TDS meters and automated butterfly valves that open and close based on the TDS level you want to achieve. But our systems, we don't have anything that blends it automatically. Most of the systems I have seen that do blend it, it's simply, like I said, it's a ball valve or some sort of flow restrictor that's cracked. cracked open, and a solenoid to shut off the whole system. So you have some level of control over it if you're able to manage the RO system, but if you're looking for down to the milligram per liter TDS level, then you're looking at something a lot more expensive. Think that's it. So once again, thank you all for spending the time here with us today. I hope you took a screenshot of our contact info there. Worst case scenario, you can jump to the end of the presentation later on and get our emails and phone numbers there. With that, I hope everybody has a good afternoon or morning or evening wherever you're from, and make sure to sign up for updates on future webinars, so that way you can be aware of anything that we share going forward. And yeah, once again, thanks for coming. Take care.
Everyone, take care.